the switch.
Right,
And everyone
okay.
will- I'll just leave it on. If you ever need to move it, you know, just same thing.
Sure.
All right, so just go
Thanks
anywhere on
very
your
much.
shirt and follow.
Should be okay. This
Yes.
height.
Yeah, that's perfect.
Cool.
No, I know you're kind of like a stand-in, but like, are you okay with your talk being recorded?
Oh yeah, no problem.
I could go.
This about right?
Hey,
time to begin. So we have a lecture this morning. I'll introduce Stephen in a minute. First of all, Yvon, as you may know by now, is sick and wasn't able to come to give her series on braids. She will, however, I believe, send her slides, and they will get posted on our web pages, and they'll be there for future archiving as the rest of the talks are. In addition, I hope maybe at some time in the future, and this may be after our program ends, to have her come live and actually give the lectures here, in which case those who are in the local area could see them live and the rest will be available by Zoom. So we are lucky to have Stephen Amelotte, who has graciously accepted to come in and fill in at the last moment and give his lecture on moment angle complexes associated to linear resolutions. So, Steve.
Thanks, Paul. And thank you for being here.
Oh, well, welcome to online people. The same message as Stephen is about to give his lecture on, anyway.
Can you guys hear me okay? No, I do. I do. But can you hear me all right?
Can you hear Stephen online? Yes, we can.
Cool, thank you.
Great, thanks very much.
All right, so like Paul said, this won't be about braids, so I'm sorry you're getting me this morning instead of Yvonne. You're really missing out because she's a great lecturer. And this won't be about configuration spaces either, but configuration spaces are just certain subspaces of a Cartesian product. And Ben's been telling us about a lot of work that Fred did on configuration spaces, like in his thesis, so right at the beginning of his career. And what this talk is going to be about are some other subspaces of Cartesian products that Fred was very interested in toward the end of his career. And I'll start with the general definition. I mean, another sort of parallel maybe with configuration spaces, that they're very simple to define subspaces of a Cartesian product. But as soon as you start asking about their algebraic topology, things get interesting pretty quickly. And also, like configuration spaces, they're already interesting when you're considering subspaces of just a product of disks. And that's what these objects are going to be. So I'm really going to focus on like a sort of simple looking example. But for the general definition, we just need 2 bits of input. So throughout the talk, let K be a simplicial complex on M vertices. So I'll always write my vertex set like this. So K is just an abstract simplicial complex, right? A set of subsets of our vertices, which is like down closed, in the sense that if sigma is a face of K and tau is a subset of sigma, then tau should be a face of K as well. So that's all. And then a pair of spaces. So, okay, let's not right below here. General definition of a polyhedral product goes like this. Let X comma A be just any pair of spaces, want them to be pointed. Usually it'll be like a CW pair. So X is a CW complex, A is some subcomplex containing the base point. Okay, and then first, for just any subset sigma of our vertex set, let's define XA to the sigma to just be the following subset of an M-fold product of the X's. So this will just be product 1 through M of a bunch of spaces yi, where each space is either going to be X or A. The X when I is contained in this subset sigma, and A otherwise. Okay, so we're just looking at the set of all m tuples of points in X. The only requirement is that the ith coordinate has to lie in the subspace when I is not present in this face or this subset sigma. And then what's called the polyhedral product. I guess associated to a simplicial complex K. Is denoted like this. We can raise any pair of spaces to the power of a simplicial complex, and the definition is just a union or a colimit over all the faces in K of these products. Okay, so that's the general definition. So notice this is just carving out some subspace of that product. And this talk won't so much be about this, but the first example to think about, simplest case is when your subspace A is just a point. So what happens here? Think of all the simplicial complexes you can have on a given vertex set. So we just have like m points. It's the smallest simplicial complex. At the other end of the spectrum, we have like the full simplex on m vertices. That's an m-1 simplex. In this case, what's happening? A to the K. There's not many faces here, right? The only faces of this simplicial complex are like the singleton sets containing each vertex. So my union is just going to have like one piece for every vertex of K. So union I1 through M. And each piece there is just looking like a bunch of points everywhere. And then an X somewhere, right, in like the ith position. So you take the union of all those, and that's just the definition of the wedge. So this is the M-fold wedge, X with itself. Well, I'm just defining a simple case, yeah. In general, there's no reason that all of these X's and A's should be the same, right? I could just take a sequence of pair of spaces, Xi, Ai, so one pair for every vertex in your simplicial complex. And then these things would all be subsets of a Cartesian product of Xi's. But all the examples that come up in toric topology that I'm going to talk about today will be of this form. Okay, yeah, and then down here, it's easier to see that the polyhedral product is associated to a simplex. That's just giving you the ordinary product. So like in this colimit or this union, notice that sigma being a subset of tau implies that this product will be a subspace, the one associated to tau. So I could really just take this union over like the maximal faces of K. And this simplicial complex has a unique maximal face, which is just the whole vertex set. Right? So in that case, this is just looking like a product of X's in every coordinate. Okay, so yeah, this simple example is just giving you like a functorial and combinatorial interpolation between the coproduct, i.e. the wedge, product, and pointed spaces. But you could do this in other categories, right? Like I said, I'm writing this as a union, but that's just a finite colimit. So any category in which you have finite colimits and products, you could do this construction. And This example gives you some functorial interpolation that goes between the categorical coproduct and product. Okay, so there's lots of other familiar constructions that you can get as polyhedral products right here, like example, the second biggest simplicial complex on M vertices would just be the boundary of a simplex. And there, this corresponding polyhedral product is the fat wedge. Ever heard of that? You can get joins and all kinds of other examples. Maybe I won't write down. But another parallel with configuration spaces is that you can also get classifying spaces of right-angled Coxeter groups, right-angled Artin groups, and their commutator subgroups from polyhedral products. So this may be similar to the fact that you just take a configuration space and a product of disks, and that gives you a classifying space for like a braid group. Okay, let me just get right to the examples that this talk is actually going to be about, though. So for topology, we have the following main players. So first, moment angle complex of the title. It's denoted like this, Z sub K. And it's defined to just be the polyhedral product associated to the pair D2S1. So maybe I should say that I'm always going to think of a disk and a circle and tori in a very concrete way. So D2 will always be complex numbers of length n most 1. S1, it's boundary. And whenever I say torus, I'll always mean the compact torus, which is just this product. Okay, so that's just a way of letting our simplicial complex carve out some subspace of a polydisk, this M-fold product of disks. And then the other one is called the Davis-Januszkiewicz space. This will be less important for this talk, but it's DJ, and it's just defined to be polyhedral product for the pair CP infinity, comma, a base point. So it's like one of these. To the K, yes, thank you. So similarly, that's just going to be something that sits between the M-fold wedge of CP infinities and the M-fold product of CP infinities. So it's sitting in here, but notice since CP infinity is the classifying space of S1, a product of those things is the classifying space for a product of circles. So I can write that is a subspace of the classifying space of a torus, BTM. Okay, and this is maybe a hint that these two things are related by a torus action. So in the moment angle complex, it's just a subspace of here, and we have an M-fold or an M torus acting here just by coordinate-wise multiplication. The M torus acts just by rotating disks coordinate-wise, and it's easy to see that that action restricts to an action on here. Coordinate-wise. The moment angle complex is just some finite CW complex. It's simply connected, but it comes functorially with a big torus action. And the Davis-Januszkiewicz space turns out just to be the homotopy quotient or Borel construction associated to that torus action. So this gives us a fibration or a homotopy fibration. From ZK to DJK to BTM. The homotopy quotient, I mean, this action isn't free in general. So the actual orbit space may not be a well-behaved thing. So in those cases, we take the homotopy quotient or the homotopy orbit space. The idea is you free up the action, right, by taking a product with ETM, which by definition is a space with a free torus action, and then we quotient by the diagonal action there. Okay, so you can think of this as coming from the left-hand side. We have a torus action, we quotient, we get this Borel fibration. So this is just a polyhedral product model of that Borel fibration. Or you could start on the right. Notice, okay, by definition, the Davis-Januszkiewicz space is just a subspace of here. So this is that inclusion. And then you look at its homotopy fiber, and you can show that that's the moment angle complex. Okay, so this fibration will sort of be important. Think of it as some fundamental object of study in toric topology that just comes functorially from a simplicial complex K. Okay, maybe I should give an example before I list some properties and convince you why you might care about these spaces. So let's just look at 2 points. So the boundary of one simplex. Just 2 points labeled 1 and 2. And what does the definition of the moment angle complex say to do? Okay, I only have 2 faces. So I'm just looking at a union of 2 things. For the first face, well, it contains vertex 1 and it does not contain vertex 2. So I'm supposed to put a D2 in the first coordinate and a circle in the second. And for the second piece of the union, the one associated to this face, well, this face contains vertex 2, but it does not contain vertex 1. So I'm supposed to put a S1 here and a D2 here. But that's just the boundary of D2 cross D2. It's homeomorphic to the boundary of a 4 disk. So we get a 3-sphere, the first non-trivial example. Yeah.
You should mention that the boundary of D2 cross D2 in the subject is very different from the boundary of D4.
Yeah. We're going to want to understand the homotopy types of these spaces, and sort of the whole idea of polyhedral products is to think of everything in life coordinate-wise. So it's better to think of the 3-sphere as the boundary of this thing than the boundary of D4. Okay, I want to maybe list some other quick examples, but first, here are some general properties. Okay, so first, I've just said these are some CW complexes in general, right? Subcomplexes of this thing. But if K is a sphere triangulation, like that example, it's the only triangulation of the 0 sphere. But in general, if K is a sphere triangulation, say K looks like n-1 sphere, and the associated moment angle complex is a manifold. It's going to be a topological manifold of dimension m plus n. So m being our number of vertices and n this dimension of the sphere here. And this talk won't really be about this, but I should mention that every toric or quasi-toric manifold in the sense of Davis-Januszkiewicz, do they put a hyphen? Maybe not. Quasi-toric. I'll say something about what this is in a moment. Okay, so I have to mention this property because to some people, toric topology is all about the study of these manifolds. A toric or quasi-toric manifold, some huge class of manifolds introduced by Davis and Januszkiewicz in the 90s that sort of started this whole subject. And the idea of them is that they're just a broad topological generalization of toric varieties. So there are some even dimensional manifolds with a half-dimensional torus action such that the quotient can be identified with a polytope. So it doesn't really matter, but all of these things, it turns out, occur as the quotient of ZK by some subtorus of this big torus action that comes with it. So the idea is, here's our main fibration, ZK, to djk. I guess I'm not going to exactly write this fibration, but pull it back one step. The fiber, this map would be the loops on there. So here's like principal torus fibration that comes from there. I said this action is not free in general, but often you can find a freely acting m-n torus sitting in there. And now if I quotient ZK by that smaller torus, remember saying this is an m plus n dimensional manifold. The quotient by this free action should be like m plus n minus m minus n dimensional manifold. Quotient Tm by this subtorus is going to be another torus, rank n. So that's your half-dimensional torus action in the case of a toric variety. Okay, so this vibration is that one, and the point here is just that ZK and this map plays a kind of universal role in the subject where every toric manifold is the quotient coming from this one torus action, right? So over a given polytope, or I guess I should say for a given like K, sphere triangulation K, there could be lots and lots of toric manifolds associated to it, but there's only one moment angle manifold. And all of these are just quotient of it for some different subtorus action you could choose here. And in particular, moment angle complexes just control the homotopy groups of all of these kinds of manifolds, for example, right? If you look at the fibration, this horizontal one, look at its long exact sequence, you see that the higher homotopy groups of all these manifolds are just exactly the homotopy groups of ZK. Okay, since I didn't, this isn't like the definition of a toric manifold, so let me just say these include all what are sometimes called symplectic toric manifolds that arise in symplectic geometry, or more generally, all smooth projective toric varieties. And lots of manifolds that aren't varieties, and in particular, certain non-Kähler manifolds. Like CP2 connects some with itself. This is just a typical example of a space which is known to not admit any symplectic structure. So it's not actually these kinds of objects, but it is a nice even dimensional manifold with a nice half-dimensional torus action that has a lot of the same topological properties as toric varieties. Okay, questions about any of this basic setup so far?
Are there any questions online?
So like I said, the talk is really going to be about we'd really like to understand these moment angle complexes in general, or moment angle manifolds when K is a sphere triangulation, because they play this sort of universal role in toric topology. So the rest of the talk will all be about getting at the homotopy types of these spaces. And I just wanted to give one more example to show you that they can be more complicated than this. So this is sort of a typical family of moment angle manifolds to show. Sorry, maybe I'll do that in 1 second. One more property, that was property 2. So let me just quickly say ZK defined to be a polyhedral product associated to D2S1 is homotopy equivalent to the polyhedral product you would get if you put a C comma C star in the definition. Right, so a disk comma a circle is of course homotopy equivalent to C comma C star, where C star is just the punctured complex plane. So as you would hope, this construction is functorial enough that it induces a homotopy equivalence here. And if you think of the definition of a polyhedral product for this pair, this is exactly the complement of a coordinate subspace arrangement that can be associated to any simplicial complex. So the theory of subspace arrangements is sort of a standard way to associate an arrangement of linear subspaces to any simplicial complex. The idea is this complex space, and we remove a union of subspaces, one for each non-face of K. So for any sigma, this is just going to be the M tuples such that I guess Z sigma 1 to Z sigma P, those are the elements of this set sigma, are all 0. Right, so you just look at all points where those coordinates vanish for any subset sigma. It's just some arrangement of subspace, complex coordinate subspaces. And then the complement of that is some interesting space. So subspace arrangements, one tries to understand the homotopy types of these things maybe, which is usually out of reach. How other topological properties of this complement depend on like the combinatorics of the subspace arrangement. So this thing, notice, comes now with a C star action instead of a compact torus action, making this thing an affine toric variety. So I said that one reason maybe to care about moment angle complexes is that you can get all smooth projective toric varieties as quotients of them. But you can also, up to homotopy, think of this thing itself as an affine toric variety. ZK is sort of a compactification, a nice compactification of this object, right? We've compactified this non-compact thing to just a finite CW complex, and we've also compactified the group action. I should throw in another quasi here. We're going to give Tony a heart attack.
That's a different context that Braid showed us, right? Define means a set of break equations, define space. It's complementary.
Okay. Thank you.
Stephen, You might mention that the homotopy equivalence between that and the moment angle complex is not obvious.
Yes, in fact, yeah. So this is easy to see just because both of these spaces are defined as a co-limit of a very simple diagram where every object in the diagram just looks like a product of either D2s and S1s or Cs and C stars. So since those are like object-wise, clearly homotopy equivalent, the co-limits will be as well. But even better, if you wanted to know that this thing is really like equivariantly homotopy equivalent to this, you have to know something more. So it's also true that this is an equivariant retract, deformation retract, this thing. So that's a slightly harder thing to prove that you can find in Buchstaber and Panov's book on toric topology. Thank you. So maybe now I can just quickly mention these examples. So over here, you might have already noticed that more generally, K is the boundary of any simplex. The exact same computation here gives us the 2n plus 1 sphere. This one, yeah. So some examples. Since that's the only triangulation of a zero sphere, we could start looking at triangulations of one spheres. So those are also simple, right? There's only so many of them. They're all just looking like the boundary of a polygon. So here we should get a 5 sphere. And then another good exercise is to work out this example just straight from the definition. You should be able to see S3 cross S3 is this moment angle manifold. And then here, this is not so easy to see, but you get a connected sum, 5 copies of S3 cross S4. So this is really just to impress you with the fact that already for some very small simplicial complexes, you get pretty interesting manifolds and not really a clear pattern of what's going on here. There actually is some pattern as we move on and look at bigger polygons. We're always going to get some complicated connected sum of sphere products, it turns out, for this family of examples. And this is really one of only a few families of examples of sphere triangulation for which we understand the homotopy type of the moment angle manifold. So let me mention here a theorem of Santiago Lopez de Medrano and Sam Gittler. (2013), I think. It says for any of these guys and more generally for any stacked polytope, I'll say what that is in a moment. So if you start with a simplex of any dimension, you take its boundary and okay, you get the boundary of a simplex, we know what happens there. But you could also start with a simplex and then just start stacking other simplices onto it by gluing facets together, and then take the boundary of that polytope that you get. That'll be a simplicial complex, and that's what I mean by a stacked polytope, right? So we start with this triangle like filled in, and we start stacking other triangles on in any order, taking the boundary. Of course, we just get all the other polygons. And more generally, you can do this in any dimension. And you get some connected sum of sphere products, it turns out. So I haven't given you, they actually figure this out explicitly, like how many summons and what spheres show up and everything. I'm not going to write that down, but here's a interesting simplification, which goes back to Coxeter in the 30s. Just this case, if K is the boundary of an M-gon, an M-sided polygon. There's a real analog of a moment angle complex. It can be thought of as the fixed points of a C2 action on here. So ZK is a subspace. This product of disks, you can think of complex conjugation acting on the disk, which is horizontal reflection. That restricts to an action here. So if we take those fixed points, then that turns out to be exactly this polyhedral product, where you use a one disk, a line interval, its boundary, instead of D2, S1. So Coxeter looked at these things and found that this is a surface oriented of genus G equals 1 plus m minus 4 2 to the m minus 3. So here you can just see that the genera here are agreeing. We've simplified the problem by sort of collapsing all these spheres just S1s, right? Notice a surface like this is just a connected sum, a G-fold connected sum of S1 cross S1. So more generally looking at these manifolds, the problem becomes more than just a homology or Euler characteristic problem to work out the dimensions, spheres that show up. Yeah.
It's the same Coxeter whose piano is out there for those of you who haven't noticed.
Yes. Yeah, there's really a lot to mention. So let's now maybe move on to the cohomology of these spaces, and that'll show how torsion can arise. So yeah, this was, I said, supposed to show you that these things are complicated, and it's not a trivial matter just to use this definition to understand the topology of these spaces or identify them in some way. But they get much more complicated than this. Right? These all have, they're all torsion-free, homology at least. But you really see how big this class of spaces is once you see what their cohomology is, because the cohomology groups can pretty much look like anything you want. So you get a surprisingly huge class of homotopy types just by letting a simplicial complex carve out a subspace of a product of disks. Okay, so yeah, cohomology. Moment angle complexes. So here's where some commutative algebra is going to come in. I don't think I said in words, this is all joint work with Ben Briggs. He's a logical and commutative algebraist. Here's a recent preprint. So this is where you'll see why I'm working with a commutative algebraist to study these things. So remember, K still our simplicial complex on M. And well, I drew some diagram during the graduate school on polyhedral products, which maybe I'll repeat now. So here's the world of combinatorics. And combinatorial commutative algebra is all about starting with some combinatorial input, like a simplicial complex K, and associating various rings to it, and then studying the interplay between those rings and the combinatorics of the object defining it. And torque topology sort of gives us a lift of this picture in the sense that it'll give us a bunch of spaces that geometrically realize these rings that are like fundamental objects of study in combinatorial commutative algebra, or the area of it known as Stanley-Reisner theory. Okay, so now introduce some more notation. So K is still a simplicial complex and vertex at M. I'm going to write S for the polynomial ring on M variables, V1 through Vm. As many variables as we have vertices. Put the generators in degree 2 so that we can think of this as the cohomology of the classifying space of an M torus. And then K of K here, where little k is usually just going to be a field or sometimes the integers. This denotes the Stanley-Reisner ring. So it's just quotient of our polynomial ring by a certain monomial ideal called the Stanley-Reisner ideal. So it's a very simple looking monomial ring where the ideal we're quotienting it by is generated by some monomials, V I1 up to V IP. I1 up to IP is not a face of K. So it's just the ideal generated by all the non-faces of K. So a simplicial complex, since its downward close is determined by its maximal faces, right? If you know all of its facets or maximal faces, then you actually know all of the faces of K. And conversely, K is completely determined by its minimal non-faces, right? If you know what its minimal non-faces are, then you know what all of its non-faces are, right? Just any subset containing a minimal non-face. And therefore, you know what all the faces are. So you can go back and forth between simplicial complexes and square-free monomial ideals like this. Any simplicial complex, we just defined a square-free monomial ideal. And hopefully you can see that conversely, if I gave you any square-free monomial ideal, there's a simplicial complex, which has as its minimal non-faces exactly these generators. Okay, so there's a one-to-one correspondence there. And we just want to turn sort of a problem of reading off the homotopy type of ZK from the combinatorics of K into a more algebraic feeling problem, where now we want to understand ZK in terms of the homological algebra surrounding Stanley-Reisner rings. But the exact same information is encoded in this ring. And commutative algebraists have very nice organized ways of spreading out all the information of a simplicial complex using this ring. Okay, so I'm not done with this diagram. Just told you what the Stanley-Reisner ring is, and then a more interesting thing I like to study, the Kazul homology, or this Tor algebra of the Stanley-Reisner ring. And then we just define some spaces, right? Associated to K is the Davis-Savic space. Turns out that its cohomology is exactly the Stanley-Reisner ring. That's not so hard to see. And then more interestingly, ZK, the Momenenko complex, has this thing as its cohomology ring. So let me state that part as a theorem. Here's a very fundamental result subject to Dubiuk-Stauber-Panov and also Matthias Franz. So there are ring isomorphisms that are natural in K. Take coefficients in any field or the integers little k. So this is like a bi-graded algebra, and the dimensions, just as a vector space, a K vector space, this thing or of its bi-graded components rather, are called the Betty numbers, the Stanley-Reisner ring, and these are like the main invariants that people use to study rings in commutative algebra. And lots of other interesting invariants of this ring are encoded in this algebra for the minimal free resolution of the ring. And then there's a further result. This isn't really due to these people, but just a classical result in commutative algebra called the Hochster formula that identifies this Tor algebra of any monomial ring in a very combinatorial way. So I think I want to use I. We look at a direct sum over just all subsets of our vertex set, the reduced cohomology. Think of simplicial cohomology of just all the full subcomplexes of K. Okay, so the theorem sort of ended here, and this is something called Hochster's formula. So it allows you to understand the Betty numbers of any monomial ring. I should say maybe that the Betty numbers of a monomial ring or a monomial ideal are invariant under polarization. So there's a way of just starting with any ideal generated by monomials and constructing a square-free monomial ideal. And that doesn't change the Betty numbers. So when you're studying Betty numbers of monomial rings, you can always reduce to these kinds of rings. And then Hochster's formula is giving you very combinatorial interpretation of those Betty numbers. So here K sub U, what I'm calling the full subcomplex on this vertex set, is just like the induced subcomplex, just like an induced graph. Okay, and I said this part isn't really part of this theorem, but there isn't an obvious ring structure on this direct sum. But this can be thought of as a ring isomorphism for a certain combinatorially defined ring structure in here, which is really nice. I won't spell out. And in that case, I should add a name Baskakov. Ring structure on here is often called the Baskakov product. Sorry?
K sub I.
K sub I. Thank you, not you. Thank you, thank you. Yeah. Okay, so it's not as if said K is like a homotopy invariant of these simplicial complexes thought of as spaces, right? These all have homotopy equivalent geometric realizations, but we get very different manifolds. But the cohomology is given by not just the cohomology of K, but a sum of just cohomology of all full subcomplexes of K. So in particular, K itself shows up when I take I to be the whole vertex set. This full subcomplex is just K. So this is what I meant. This is where you can see how big this class of spaces is now. If you want to arrange to have any like sequence of cohomology groups to show up in this space, just take a space with those cohomology groups and triangulate it in any way, and then take that as your simplicial complex. And that moment angle complex will have those cohomology groups showing up. Yeah.
You said you can get torsion, but can you get torsion if your underlying K and X and A have no torsion?
If
You're saying that
X and A have no torsion?
you could build something with torsion by starting with the simplicial complex K such that its realization had torsion.
Yeah.
But suppose I restrict myself to K's where the cohomology of K has no torsion,
right,
and I use only X's and A's which have no torsion.
Right.
Can I get torsion in the result?
Yes. For example, there are sphere triangulations. So a sphere certainly has no torsion. And this is the polyhedral product associated to D2 and S1, which have no torsion. But the moment angle manifold associated to a sphere triangulation can definitely have torsion. So weirdly, you can triangulate a sphere in such a way that certain full subcomplexes, which aren't the whole thing, can look like just whatever you want. Yeah. Okay, I'm gonna run out of time for sure. This is, you can tell I only started planning this talk yesterday. Okay, and I shouldn't write below here. Okay, I won't write this then. All I wanted to say was there's some shifting going on here. So it's not like the ith cohomology group here is exactly the ith cohomology group there. was going to show an example to indicate this, but maybe I should just rush forward. Okay, well, the point here is just that the cohomology of these spaces are well understood. And even better, the stable homotopy type is also well understood. Question? Oh. Okay, so let me jump to BBCG splitting. This is Bari, Bendersky, Cohen, Gittler. The 2010 or so. They give a suspension splitting, so a splitting of any polyhedral product after you just suspend one time. So in the case of a moment angle complex, it looks like this. We get a wedge over all the non-faces of K of certain suspensions of full subcomplexes of K. So studying the stable homotopy types of these spaces isn't so different from just studying the stable homotopy types of all finite CW complexes or something. So we'll just get anything showing up over here. And notice that the suspensions here account for the shifting I mentioned. So I didn't write down exactly how the nth cohomology here corresponds to like which cohomology groups here, but this indicates maybe how that happens. It's because there's a lot more suspensions on this side than there are on this side. The low dimensional cohomology groups of any of the full subcomplexes here tell you about higher dimensional cohomology groups of ZK. So this splitting recovers this classical theorem from commutative algebra, Hochster's theorem. Right? You can prove this completely at the level of spaces. Right? I apply cohomology to the splitting, and I get exactly that second thing here. Notice this sum is over all subspaces of M, but I may as well have just summed over the non-faces. If I is a face of K, then the induced subcomplex is just a simplex, which is contractible, so it's not really contributing to cohomology. Okay, so we'd really like to now understand the unstable homotopy type, right? Especially for sphere triangulations. A manifold is never going to look like a wedge like this. So most of the information is contained in the unstable homotopy type of ZK. So an algebraic problem is to ask when is a ring, like a Stanley-Reisner ring, Golod, and this means when is this Tor algebra as simple as it possibly could be in the sense of being trivial as a ring and also having trivial like higher structure. So all products, Massey products, vanishing. That's what Golod means. So most like celebrated results in combinatorial commutative algebra say things like this ring has such and such a property, like it's Cohen-Macaulay, precisely when K has this combinatorial property, or this ring is Gorenstein, precisely when K has this property. So certain like very common words in commutative algebra and homological algebra have beautiful theorems like that where things work out. And then other very common words like this one, there doesn't seem to be any nice combinatorial characterization. So this is a hard problem, and we get a topological analog when we think of these moment angle complexes. So for which K does ZK have the homotopy type of a wedge of spheres? Gola just means the Tor algebra of this thing is as simple as it possibly could be. And the simplest homotopy type that a moment angle complex could possibly have is a wedge of spheres. So this is, there are just very natural topological reasons why the cohomology of a space would have no cup products or higher Massey products. One of them is like this, or ZK is a suspension. Topological point of view, these are very natural reasons that would force this to be Golod. But they don't correspond, they don't seem to correspond nicely to any concepts in commutative algebra. It's not the case that ZK being a suspension, for example, is equivalent to this ring being Golod. I think this is maybe a good thing. It's potentially a useful perspective. We might have some way to help. So I should give some sort of history here. There's been a lot of work on this problem. Most of the work in trying to study the homotopy type of moment angle complex is focused on identifying when the simplest possible thing can happen. So let me just state like an omnibus theorem, or here's a bunch of theorems really due to a bunch of people. Grubich, Terrio, starting in the early 2000s. Alker. Recently, Irie and Kishimoto. (2019), I believe. They all looked at certain classes of simplicial complexes, showed that this happens. So if the Alexander dual, K dual, which is defined to be just the complements of all non-faces of K. Okay, so if K is a simplicial complex, look at this set of subsets of the same vertex set, and that'll also be a simplicial complex. It's called the dual, or the Alexander dual. So if that thing belongs to any of the following classes of simplicial complexes, then ZK splits as a wedge of spheres. So this result started with simplicial complexes called shifted. This case was also covered by some early work of Irie and Kishimoto. They sit inside a larger class, vertex decomposable simplicial complexes. That case corresponds to these authors. Sort of eventually realized that these all sit inside a wider class of called Cohen-Macaulay complexes. And a shellable simplicial complex, whatever that is a typical example of a Cohen-Macaulay one. And then slightly more general than that, Irie and Kishimoto considered this bigger class of sequentially Cohen-Macaulay simplicial complexes. So these are all, or these anyway, all have some combinatorial definitions I'm not going to tell you about. This is a more homological definition. There's this long sequence of results that went like this. And these all recovered existing results in the commutative algebra literature, identifying classes of complexes for which the Stanley-Reisner ring is Golod. So these can be thought of as like an improvement of those results or a lifting those results in commutative algebra up to the topological setting. Yeah. It's not in the Stanley-Reisner ring, thank you. Thank you very much. Really meant in Kazul homology. make more sense? Okay. So what we wanted to do was approach this problem and these theorems from a different point of view where we don't go through Alexander duality, right? All of these theorems are saying if the dual of K looks like something, moment angle complex associated to K, not its dual, as a wedge of spheres. So there's a slightly more direct way of going about it. And I want to formulate a theorem that just doesn't have any assumptions on K. We prove a theorem just holds for all simplicial complexes K and says something about the Hurewicz map. And notice, fun fact, that a simply connected space has the homotopy type of a wedge of spheres precisely when its Hurewicz map is surjective, like for all coefficients Z mod P, say. Right? If every homology class can be represented by a sphere mapping in and hitting it, then you can just take a basis of homology, pick a bunch of spheres that map in to hit those basis elements, wedge them all together, and you get a homology equivalence and therefore a homotopy equivalence. So I could either right here at the end spell out that theorem, or we could break. Maybe people want coffee, and then I definitely am not going for 2 hours, since this isn't a.
Why don't we take a vote? Who would like to take a break and then come back?
I'll only go like maybe 15 minutes more. I don't want to subject people to 2 hours of like a research
So
talk.
who would like to have Stephen finish? I think let's see the break people again. Who wants a break? Oh, now it's ambiguous.
Well, I think the people who want coffee should maybe trump the people who don't care. Maybe we very quick break for coffee.
Let's have a quick break. There's a beautiful lecture, right? So why don't we have a quick break and come back and enjoy more beauty? Yeah, okay. Okay, for those of you online, let's have 15 minutes. Hey, Anna.